I think this video is going to end up being a bit spicier than some of my previous videos. We're taking a look at PaLM-E today. This is a new paper out from Google that takes their previous large language model PaLM, which was over 500 billion parameters, and now they're adding a few more parameters on, turn into an embodied model, PaLM-E. So this is a model that can interact with the real world. And when I first heard about this, I thought this was awesome. I mean, I literally just made a video about how one of the big issues with language models is that because they're, for example, not embodied, they can't get feedback from the environment that is grounded like to reality. And I think this is a huge issue. So seeing, like the day I post that video, this come out, I was very excited. I even had several people comment on that video asking me what my thoughts are on PaLM-E. And coming into the paper, I was super excited to see what they did with this. And then I read the paper. And I was not as excited after reading it. So I kind of want to show you what went wrong in my mind. And, maybe I'm crazy. Maybe you guys think this is awesome. I don't know. I want to show you where I'm coming from, though. So why even cover this if I, after reading the paper, wasn't too excited about it anymore? Well, it's because I am still very excited about the idea. One thing that's really cool about this paper is that it does show positive transfer. And that's where the agent is able to take its experiences from training on multiple tasks. So instead of just training on maybe one robotics task, it shows what they show in this paper is that by training on multiple robotics tasks, they can improve the performance on not just the currently trained tasks, but all of the tasks together. Essentially, the model is able to learn some general structure between these tasks that is allowing it to improve at all of them at once, which is very neat. So here we are in the paper. Let's start by talking about how PaLM-E works, what it actually is. Of course, the core of it, as I mentioned, is a large language model. And when we say large, we mean large. We mean over 500 billion parameters large. And the changes they make here to turn this into an embodied agent are actually very few. There's not too many things going on here. Just as before, different words are taken and they're basically tokenized by the transformer, fed through, and then some new text is predicted. This is essentially how transformers work, right? They take in tokens and they output other tokens. So what's actually changing here? Well, all that's changing is how the inputs work. So instead of just having text tokens, now we also have image tokens and perhaps other embeddings, depending on what modality you want inputted into this. When you do want to input an image, because transformers are set up generally to take in these text tokens, it's not clear how you would put an image in. So for this purpose, they have a few different ways of doing this. One of the methods they use is VIT, which is a vision transformer, but they also use a few other methods. So let's look at those. In this section, we'll be able to see the different ways they format these different images. The first thing they go to are these state estimation vectors, and these are just the simplest thing you could think of. They're taking, for example, if you have a robot and you have an image of the robot, maybe there's a vector describing the state of that scene. So right here, as they say, vector describing the state of the objects in the scene. So for example, it might contain the pose, size, color, or these sort of attributes of the object. So this is something that someone might either need to go in and individually label, or maybe they have a model for doing this. I'm not exactly sure how they do it, but the point is that it's sort of the simplest way of describing this without having to have all these complex models. The next thing they do is having a vision transformer. So a vision transformer is exactly what it sounds like. It is a transformer for vision. So specifically, they have some pre-trained models they use here. One is VIT 4 billion. So it's a vision transformer model with 4 billion tokens. And they also have a 22 billion variant. And then there is VIT-TL, which I guess is some other type of vision transformer for specifically learning tokens. It's not something I'm very familiar with, but it's not very core to this paper. Transformers, if this is our lovely transformer here, they're generally trained to take in sequences of words or tokens, and tokens will have some sort of semantic meaning, right? Like if I give you the sentence, the black cat, as I've done here, maybe the isn't the best example of this, but black and cat, they're both they have some sort of meaning. Black is a color, cat is a type of creature, right? And what they point out is perhaps vision transformers, they give out these embeddings that are not necessarily tokenized in this way. It's not split into different objects, even though lots of the times we can split images into different objects. If I draw you a picture of a bird with some like background, you could obviously point out the bird as being like one central figure, right? So they also introduce this object scene representation transformer, or OSRT, and this is a model that has some inherent bias in the structure of the model to kind of pull out these different objects. Again, I don't know the details of how OSRT works, but the details of how it works are not really important here, more of sort of what it's doing. It's going to be like an image. They throw it through this, I don't know what to call it. In this case, let's say it's like a VIT, right? And then it comes out the other side and they get either one output, or they might also get multiple outputs depending on the method. For example, OSRT, I think, will give you multiple outputs. And then these outputs will go through another transformation. We'll draw this for the transformation. And the final output here is the actual, I guess, well, I don't know what to call these. I already used M. We'll just use M. I don't know why. M1, M2, M3. And each of these will be an actual token that goes into the final LLM. So I just do this to say that each of these images is not necessarily being turned into one token, but a series of tokens. And the difference between each of these methods is essentially how they go from the initial input image down to these tokens. So OSRT, for example, as I had mentioned earlier, we've been focused around objects, while VIT will give you just some vector, and then there will be some transformation that splits it up into these various tokens. This is something that has been attempted before. Notably, I remember Gato was a paper from DeepMind that tried to do this. I also covered that on this channel, and at the time it didn't quite work. So I was very interested to see what they did here that would allow them to get positive transfer when before it was a struggle from other very talented people. So that should give you an idea of how we go from text and images and then pass those as tokens into the language model. But then how do we go from the language model to going to our answer? So here, for example, you can see we start with the question, how to grasp blue block. And then the answer is first grasp yellow block and blah, 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 blah. So if we're just doing a language task, all we need to do is output language, right? That's super easy. So the question is, how do we go from this language though, if we want to do robotics, as you can see happening right here? So how do we go from language models to actually controlling robots like we can see right here? And the answer is, I'm not gonna lie, it's somewhat disappointing. They just take this text and they put it into a different model. So this control box right here, it's just a different model they have. It's pre-trained. There's a different paper on how they actually do this, going from text to actions. So the actual actions are never outputted by the large language model. It's just doing the quote unquote reasoning part. I guess this is the first thing that that was a little bit of a letdown in this paper, but so be it. We can still hopefully find some very neat insights even by doing this. To go over some examples of what that might look like though, we can take a look at, well, all the examples we have right here. So first, in mobile manipulation, this is a task we'll see. So we'll go over all the 3 tasks we'll see quite a bit right now. The first one is this mobile manipulation, where they have this robot and it's just, going around the Google headquarters doing its thing, and they will ask it to do something. For example, in this case, we have human, bring me the rice chips from the drawer. Then the robot one, go to the drawers, open the top drawer. So this is all prompting. And then it gives it an image of, something like this, as you can see. And the language model is supposed to generate this. 3, pick the green rice chip bag from the drawer and place it onto the counter. So this is what would actually then go into this control module, and that would be executed by that policy. Now there's 2 more tasks that we'll see very frequently in this paper, so we'll take a look at those right now too. One is task and motion planning. So this is another robotics environment where there's a bunch of different colored cubes. It's simulated, and basically the robot has to do something. So here, given embedding, and this embedding is going to be some representation of the environment, right? How to grasp blue block. And again, we get the same thing. Now the robot answers with, first grasp yellow block and place it on the table, then grasp the blue block. And then this again would be passed into the control policy, and it would take care of that. And then the third environment we'll see, you'll notice these are all robotics environments, is tabletop manipulation. And here, again, I'll spare you going through the exact example, but it's the same sort of thing where there is some goal of maybe moving like the blue cube over here, and the LLM has to output how it would go about doing that. These are the types of tasks that will be focused on, but it is important to note that the model is trained to do other things. The idea is that by training to do other language tasks, for example, question answering or describing a certain image or writing haikus, because why not, or the typical tasks you would see in a language model, by also training on these, the idea is that will also help out with the robotic stuff because it's all in the same text domain. So learning one can hopefully help you learn another. All the training here is also done through supervised learning, which means for all of these robotics tasks, there's no real-time interaction. It's all the training examples are taken from this static data set that is gathered beforehand. So in the static data set, for example, you would have all these sentences and the image, and you would just feed these in and predict the next token like you normally would. So it's being trained just like a normal language model. There's not any RL or anything like that happening. And I feel like this is a good place to maybe address some of the comments from my last YouTube video. And all these comments were essentially asking, what do I think of Palm E? Because funny enough, this paper came out around the same day, I think, that I published the video where I was talking about how one of the big problems with current LLMs is that they're not grounded. And because their feedback is not grounded, they have trouble learning. But something like embodiment could help improve that. Because when an agent is embodied, well, then its feedback can come from the real world and it can be based on real things instead of human feedback, which is not scalable, or something else that is just not always going to be correct. So what are my thoughts on PaLM-E in regards to this? Is a step towards the human level intelligence I envision? And the answer is emphatically no, not at all. And this is one thing that I don't love about this paper, but it's not necessarily bad. This is the same thing, right? It's not what I would personally want to see in a paper, but it doesn't mean it's not valuable. So what is the issue though, right? Because in my last video, I was saying you need an embodied agent, and now we have an embodied agent, and I'm saying, no, still not good enough. I swear it's not just because I want to complain. The issue is that the agent is actually not embodied, not while it's training. As I was just going over, right? All this is coming from a static data set. All these pictures and the actual actions, it's not actually taking actions. It's just seeing actions and trying to copy them. The agent never gets to interact with the world and actually train on, taking its own actions, seeing what happens, getting feedback from that. All the feedback is, again, it's just coming from some data set collected by humans. So I don't know, I find it hard to call this embodied. It's only embodied after all the training is done, which is, I think, the most important time to be embodied. How are you supposed to ground your feedback in an environment when you're never actually interacting with the environment in the first place? So that's my take on whether or not this is a step towards human level AI. No, not at all. But maybe we could get some interesting insights. As I had mentioned earlier, one thing that this paper claims is that we see positive transfer, which alone would actually be good. Maybe I shouldn't say we can't take any steps in that direction, just not the steps I was referring to in my last video. So again, that doesn't mean this type of embodiment can't be useful. Just having something in a robot interacting with the world can be useful. And also doesn't mean we can't get interesting insights. Speaking of which, let's actually get into the results. And here we are where you can see figure 3, and this is where we show the positive transfer. What you're looking at here is you're looking at the 3 environments we were looking at earlier. The TAMP environment, as we'll call it, which is the simulated environment with the blocks. We have the language table environment, where again, you have the robotic arm moving these different shapes on a table. And we have the say can data set, which is this robot that moves around the Google office doing various things. And what you'll see is the performance if trained on each of them individually. So you can see that here, here, and here. And this is the success rate on the y-axis. So how often was it able to achieve the given task? And what you'll see is that when this model, PaLM-E, is trained on each of them individually, they all do, okay. The language table, I guess, is the toughest with the lowest rate right here. But when PaLM-E is trained on the full mixture, which is a mix of data from all of these, it actually does much better on all of these tasks. We're not taking any extra data from any one of the tasks. It's just that the data from the task is helping the other task. And this is a really cool idea. The idea that we can train on one of these tasks and then it helps out with another one, that's huge. It means that we could learn much, much faster without having to do every single task individually. And this is kind of novel. It does go a little bit beyond, I would say, what we know about language models right now. We know in language models that if you take an internet-wide text database and you train an LLM with that, it will be able to learn quickly. I think this was like the title of the first GPT-2 paper or whatever. It's like language models are few-shot learners or something like that. So it's similar to that, but it shows that we can also take things that are not language if they're structured in the right way and still see those same sorts of benefits, which is, really good to see. One question I immediately had upon looking at this, though, is why does it work so well, right? Why do we see this really strong positive transfer? For example, if we take Gato, which I might or might not have mentioned, depending on if I cut that part out or not, but Gato was a paper where they tried to do the same thing with a billion parameter model. DeepMind attempted this, and they were not able to see clear positive transfer. So the question is, what's different? And I think there's a few things that could be different, right? It could be this scale that is allowing this to happen. This is a model that is much bigger than the Gato model. I'm not sure if the one they're testing here is the 12 billion parameter model or the full 500 something billion parameter model. The original Gato model was 1 billion parameters, so this is quite a bit bigger. The other thing is it could be because of the separate vision model. I believe in Gato, they don't actually use a separate vision model. Rather, the images, you take patches of the images and you turn those into tokens to pass into the language model. So that could be helping. And another thing is it could be the pre-training, because that, again, is another thing I don't think was present in Gato, or it could even be something else. So that is one thing that is certainly on my mind after seeing this. What allows this to be so successful, where before this, in something like Gato, we did not see these results? So let's continue on with these results and see if we get an answer. Figure number 4 is what we'll be looking at next, and this is breaking down specifically the TAMP task. So this is the task, if we go back up, where we had just the one on the left here, the one that is simulated, the simulated robotics task. Except for here, we're looking at a couple more things. First, we have the LLM fine-tuned single robot. This was what we already saw before. This 49% accuracy is the accuracy when trained on just that data, whereas the LLM fine-tuned full mixture is when trained on all data, the accuracy on the specific TAMP task. So you can see, as we already saw before, it goes up. So what else do we have here? Well, notably, we have the same thing, but when the LLM is actually frozen. Previously, the LLM was not frozen. It was being fine-tuned, but if we freeze the LLM, which means that we're only training the vision portion of this, can it still adapt and do well? And the answer is actually yes, which is pretty cool. It means that the LLM has some structure, or it's just big enough that it allows the knowledge through that is required to do well here, and we still see the positive transfer. Or in other words, the ability to fine-tune is not essential to see positive transfer. And the other thing here is they have trained this model also without pre-training. So this means they would just be starting from a completely newly reset LLM and vision model. And we can see that it does a little bit worse than the pre-trained LLM. But one thing they don't show here is they don't show how this non-pre-trained model would compare to a non-pre-trained model compared with the full mixture, which I think would have been very interesting to see. Because with just this, we can't tell how important pre-training is when it comes to positive transfer. So actually, I don't know why this is here. This is the first thing I had like a question mark in my head. Like, I don't know what this result really tells us. The other thing to mention though, and this is the same for the previous result, the other question mark I kind of had in my head was it's not clear how this is trained and tested. I mean, I would assume they're taking example, rather we know how the training of the LLM works, right? They take in a bunch of text from this example in this environment and they feed it in and they predict the next token, but it's not clear how much they're training. And it's also not clear if the testing data is separate. I would assume it is because that's pretty standard, right? But like how much test data they're using, what the error bounds are on this, none of that is really clear, which is a bit concerning. Normally you would have that in a paper. I just wish they had a bit more information here to interpret these results, because they don't really explain this anywhere else in the paper aside from just right here. So really, I think the takeaway from these results is that fine-tuning in LLM can help, but also it's not required to see the positive transfer. And with that, we can move into the next results right here, and these deal with the effects of using different visual encoders. On the left, you'll see all the different types of encoders. So we talked about most of these before. The state is just sort of this underlying state. Maybe it contains positional information or something like that. Vision transformer right here. So we have the VIT plus TL, then the 4 billion variant with both the single robot data and the full mixture of data. And then we also have OSRT, which, to remind you, this is the model that outputs representations that are specific to certain objects. So maybe one of the tokens will be about, I don't know, if there's a bird in the picture, a bird, or in this case, the case of robotics, maybe it will have, something about a turtle, right? One of the representations will be about a turtle and another will be about this star. By the way, if you're enjoying this, consider subscribing, if for nothing else, for the turtle. And I think the takeaway here is that these object-centric models, so these ones in these rows, are doing the best. OSRT does the best. I think this does beg the question of why isn't something like the underlying state do the best? That's what you would expect, right? Just giving the underlying state would be the best. But apparently not. I guess something about OSRT is special. It's not something they really dive into or give. I don't think they give much of an explanation on. And then I also don't know why VIT plus TL isn't doing better. It's also doing this object-centric thing, but it's not doing very well at all compared to OSRT. And perhaps this one, I think it's because the VIT plus TL is not pre-trained, but the OSRT is pre-trained. I'm not really entirely sure. I would imagine lots of you are probably pretty confused by this point, and I think the reason you're confused is because I'm confused. I don't really know what's going on here. So this portion right here, right, is of course how these different visual encoders affect the performance. It makes enough sense. But like before this, what were we looking at? We were looking at, for this specific environment, how a frozen LLM affects this. And then before that, we were looking at this positive transfer. We're kind of jumping from one thing to the next without too much of a story behind it. To me, this paper feels like you're just jumping. And there's nothing wrong with that, right? Of course, you need to jump from one thing to another in a paper to get all these ideas across. But when I read this paper, I just don't feel the connection between them, right? It feels very disjointed, and I can't really see like the thread connecting all these different experiments. Like, I don't know what to be looking for. And then the other thing is that when we look at these experiments, what really confuses me is like, why are we, first of all, there's a lot of missing information, like VIT plus TL. They mentioned previously, I kind of skipped over it, but they say that this is not pre-trained, whereas OSRT, I think they do say is pre-trained if I'm correct. And then they also have like the single robot data here versus the full mixture data here. Like, they're comparing all these different things that don't really match up in the same comparison, it just raises the question in my mind of like, why compare these things? Why not, for example, just compare one model with the state, one with VIT plus TL, one with VIT, one with OSRT, and if one of them is going to be pre-trained, maybe pre-train all of them, or maybe I'm mistaken on that part because they don't make it super clear, or maybe this is making a lot of sense to you, and if it is, I'd be very curious to hear. Maybe I'm overlooking some stuff. I don't know. We're going to push ahead though, and we're going to see what we can extract from this paper because I think there are still some good nuggets of information. This is the last page of results. We don't have too much left to go. I will kind of glaze over some of these results going a bit fast because some of them there's not enough information to understand them, or I just don't really get what's going on, because kind of like the last one, things are just, they're confusing me. They're a bit weird, but I'll still do my best to explain what I understand. So in this first table right here, what we have is, again, another embodied robotics task. So this is, I think, another simulated one where the robot is moving around some different shaped objects again. And this time we're looking at few shot learning because we have a number of demos here. And you can see we range all the way from 10 demos up to 40 demos for task 1, or all the way up to 80 demos for task 3. And the different tasks you can see on the right here. So I'll just read out the different tasks so you have an idea of what this agent is trying to do. One is, there is a block that is closest to the sum area. Push that block to the other block of the same color. The second task is how to sort the blocks by colors into corners. And the third task is how to push all the blocks that are on the left or right side together without bringing over any blocks that are on the other side. So what they're trying to do here makes sense to me, right? They're trying to see if it can few shot learn. Why they're trying to see if it can few shot learn, I don't know. I guess that would be an interesting thing if it could, right? And what they show is that, performance gets better as you do more demos. But what's not clear to me is you can see the matrix of the different models they're comparing right here, right? Like whether or not they're fine-tuning on the task, whether or not the LLM is frozen, whether or not the LLM and the VIT are pre-trained, and whether or not this is all being done from scratch, which, I mean, these two are just the same thing. So I don't know why they have both of these columns, but it's like you can see there's no like structure to this. It seems like it's kind of madness. And then they also have an 84 billion parameter model, but then all the other ones are 12 billion. And only one of these is learning from single data and the rest from full mixture data. So I don't know why these are the models they're comparing, but so be it. And the other thing that I think would be helpful to know here is for this few shot learning, are each of these examples only being trained on once, or are they being trained on multiple times? Because if they were improving this fast with only being trained on once, for example, going from 31% accuracy to nearly 60%, well, that would be pretty impressive if you're only showing 20 examples and only training on them once each time. But if you're taking those 20 examples and you're training on them continuously for many, many epochs, I don't know, is that as impressive at that point? I don't know. For table 4, this is one of those ones I'm just going to kind of glaze over because, I mean, it's the same thing as the previous one. I mean, it's not. They're testing a different thing. I can at least tell you what they're testing, which is they're trying to see how well a model can detect failure and how well it can detect affordances, which are things that the model is able to do, because an embodied agent, right, there's some things it can do and some things it can't. So an affordance is saying, can it predict what it's actually capable of? And again, they compare various models. I'm not sure why these are the specific models they're comparing, but alas, these are the ones they do compare. Perhaps one thing at least I can point out is here for the failure detection, there is no positive transfer apparently. And for the affordances, there seems to be, but at the same time, we don't know how much training data they're using. And previously, because the gap for the positive transfer was big enough, I was willing to believe it even without like some confidence intervals or knowing how many examples they use. But here, I don't know how many examples they're using for testing. And because this difference isn't as large, I'm not as confident saying that there is positive transfer happening here or not. We are going to skip over table 5 because they are just doing normal vision question answering. There's nothing embodied about this. I don't know why they include this. I think they even mentioned the paper. They're like, this is not very core to the paper, but we threw it in here anyway. I'm like, okay, I'll just skip it then. So we're going to skip that. But finally, we get to figure 6, which I think is actually a little bit interesting. And it has to deal with catastrophic forgetting. Catastrophic forgetting is, let me erase this, is this idea that when you have a model, it has limited capacity. So it's inherently going to have to forget things as it learns more. Eventually, right? Eventually it will have to forget things. And this is a big issue because if you want to learn how to do many different tasks, well, you're going to have to forget stuff eventually. So how do we avoid catastrophic forgetting, or at least sort of alleviate it? Because we will have to forget at some point, but perhaps we can try and mitigate that to some point. And what they show here is that as your model gets bigger, so they start with the 12 billion parameter model. then they go to the 84 billion parameter model, and finally the 562 billion parameter model. And they compare the blue ones, which are the embedded models. So these are the embedded models, and then the orange ones are the normal models. So these are the palms before they add the extra stuff and the extra training. And they show that there's this huge decrease in performance on the embedded models when they just go back to normal language tasks, as you can see, but that shrinks as the model gets bigger, essentially meaning bigger model means less catastrophic forgetting. But I think this is already something that is known that other people have looked at, that as your model gets bigger, you experience less catastrophic forgetting. I'm not sure if it's explicitly been looked at or not, but certainly it's been something I think that you could infer. So I think this is a very interesting topic, but what I think is unfortunate is that this is all they give us, and it's unclear how much training the PaLM-E models are doing. Like, is it just the 100 examples that gives us this decrease, this almost 90% decrease in performance? Because if they're just training on like 300 examples, which is how many examples they're using, I think, from each of the robotics tasks, and they're only training for one epoch, this is a huge decrease. Like, we should not expect this level of decrease. But if they're training for like hundreds or thousands or, I don't know, hundreds of thousands or epochs, yeah, it would make sense we would expect a big decrease. So what I think would be very interesting here would say, how does this scale with the amount of training, right? If we're going to train on like maybe 10 other tasks and we're going to train X amount on each one, we see an N% decrease in performance or that much catastrophic forgetting. But if we train only half that amount on these tasks, then we see this amount. And you could sort of get some idea, right? You would be able to plot some graph. On the x-axis, you have like amount of training, and on the y-axis you have the decrease in performance. And what you would see, hopefully, is something that goes down, right? The more you train, the worse your performance gets, but you would kind of be able to see how it scales. That would be interesting, right? That's not really what they show here. They just show that bigger model means less catastrophic forgetting, which is already, I think, known. So I feel like there's a lot more potential in this, but yeah, and those are the results from this paper. So I think, we can sit here and be confused, or we can kind of look through this paper and say, what can we take away from this? What are the good things that this paper did that we can take away from? For example, like the positive transfer stuff is very interesting, I think. It's a very interesting, cool thing that they did. I'm going to give my own thoughts and what I think the takeaways are. But before that, I want to take a look at the conclusion that the authors themselves gave and see what they think their work is adding. So I'll just summarize this first portion right here, because it's all it's basically saying is we made this PaLM-E model and it can be in robots and works in the real world, and it does better than some of these previous methods. Okay, sure, cool. It is I guess state of the art in these methods. I don't know. I don't really keep up with what is state of the art, but if they say so, I'll trust them on that. The next thing they say is that OSRT works very well even without large scale data. So fair enough. I don't know if anyone else has tried to use OSRT in this way. They say this is novel. So sure, I do think this is something interesting. They showed that this worked better, though I will say it was kind of hard to tease that out because all the comparisons were between, like, it wasn't clear if the models were pre-trained or not, and that made it a little bit confusing. The other thing they say is that diverse training leads to several avenues of transfer from visual language domains to the embodied decision making, enabling robot planning tasks to be achieved data efficiently. Sure enough. So, true enough, they do show that positive transfer does occur. And the last thing they mention is that frozen language models are a viable path towards general purpose embodied multimodal models that fully retain their language capabilities, which essentially here, I guess they're pointing at the fact that by freezing the language model, they can avoid catastrophic forgetting and not have to worry about that while still getting okay performance. That being said, the performance of the frozen language models was not nearly as good as the models that were fine-tuned. So sure, it's one way, but I think they showed themselves that it's not the best way. So whether or not it's a viable path forward, I'm not really sure. If you want like general purpose things that can do a bunch of things, I think they're going to need to adapt all these things. So I'm not sure I even agree with what they're claiming here. They showed that it can work, but far from perfectly. And they say they have also surfaced an alternative route with unfrozen models. Scaling up the language model size leads to significantly less catastrophic forgetting, while becoming an embodied agent. So this is what we were just looking at, right? This idea of having less catastrophic forgetting. That being said, here they say they surfaced an alternative route. Did they surface this? Is this new? If this is new, this is news to me, because I was pretty sure of this already. But I don't remember, to be fair, I don't remember where I read this or if this was something I had just assumed. But I'm not sure this is really new. But true, yeah, sure. You can scale the model and you're going to get less catastrophic forgetting. But also, this is only a fraction of what we're going to want our agents to do, right? Like how big are we going to need to make our models if we want no catastrophic forgetting, but we also want them to do a bunch of really high tech tasks? I don't know. They'd have to be pretty big. And then finally, they show that their final biggest model, Palm E562B, can also do some other cool things like chain of thought reasoning, blah, blah, blah. I kind of skipped over those parts. So, but yeah, sure enough. So yeah, that's what the authors say their main contributions are. What are my thoughts on this? You might already be able to tell. But let's start off with the good. Positive transfer is great. Being able to see that happens is really cool. But I'm still left with the question of like, why does it work? And to some extent, just being able to get something to work is very important. But if you don't understand why it works, you might not be able to get it working again in a different situation, right? Like unless Palm E is going to be the model that gets us to AGI, we're probably going to want to get positive transfer out of the other models we build. And to that extent, it would be very useful to know how we go about doing that. Is it just scale? Do we not have to worry about any of these other things Palm E did? Because if that's the case, that would be good to know. Or if the scale doesn't actually matter, but it has to do with the way that they have a separate visual model that is, the vision model precedes the LLM, that if that's all we need, then that would be great to know. And another question is, does that even work for non-supervised learning? This whole paper was still supervised learning. If we go into a harder type of learning like reinforcement learning, does this still work? Who knows? The other good thing is that we saw catastrophic forgetting happens less as models scale up, but we still don't know how that scaling happens. And it still doesn't seem to me like scaling up, unless we get models that are a lot bigger, that just scaling up will be able to mitigate this sort of catastrophic forgetting enough. But I still can't say that confidently because they don't tell us how much training they did. At least I don't think, unless I overlooked it. They don't tell us how much training they did that evoked that level of catastrophic forgetting. So again, that's really not something we can answer because the paper doesn't have those details. Overall, I think maybe you can understand why I said this was going to be a bit spicier than most of my videos. I think this paper had a number of issues, to be frank. That isn't to say it's bad. To me, this seemed more of an engineering project because if you actually look at the final project, having a robot that can go around, do things based off textual commands, look at its environment, see what it can do, see what it can't do, give instructions, like that is very impressive. It's very neat. And I think the final system they ended up with was very cool. And it seems like that was really the focus here. The fact that they just got this to work, but then they tried to write a paper around it, and the paper just, I couldn't really see what they were going for. I would love if they would do a follow-up paper on this, taking this model and looking more deeply into these positive things they found. I think it'd be a super interesting follow-up to read, so we'll see. We'll see where this goes from here. Either way, it was interesting to read. Curious to see where this stuff goes. Thank you so much for watching, and I hope to catch you next time.